Okay, algebraic reasoning. Today we're going to be talking about different types of parent functions. So the first thing is what is a parent function? So we have several different types of functions that exist. The one that you're probably familiar with or most familiar with is the one I'm drawing right here, which is a line. Okay, so we can take this line and we can move it around, right? This line doesn't have to exist here. It could also exist up here. Right, we can shift it up here. We can shift it down here. Right, we don't even have to keep it with the same sort of slope, right? It can be steeper. We can also make it less steep. There's just a lot that we can do. We can shift it to the right, right? We can shift it. I already used orange. Green to the left. There's just a lot we can do, okay? So our goal today is to just become familiar with each of these. And the reason why it's called parent function is all these other graphs that I drew besides the dark blue one are all minor deviations from the blue one, right? So it's like, you know, obviously you have a mother, and so you have a father, you have a parents, right? And you're not exactly like your parents, but you're similar. So that's the idea. We have functions that we call parent functions, which are the default one, and then from that we create deviations. So today we want to figure out what those parent functions are, and the real goal here is that you really want to have these shapes in your head, because at the end of the day, when you progress into future math courses, it's going to be they're going to have to assume that you already know what these functions are. So let's do that. So the first one is y equals x. Now, the big thing I also want to stress today is what is the function? What does it look like? How do we know what it looks like? And the easiest way to tell what the function looks like is to just plot points. So if we have x, y, we're just going to plot points, -2, -1, 0, 1, and 2. And so if x are these values, if x equals y, the y is the same thing. And so when we plot this, we can go, let's say this is -2, it's -2, then -1, then 0, then 1, then 2. So it's going to look something like this, okay? Now, we're going to talk more about this later, but I do want to just run through it right now real fast. There's this thing called the domain. The domain represents the x values. And so the next question is what are the x values? X ranges from what to what? Well, this function shoots to the left forever and ever, and also to the right forever and ever. So we know the domain is going to be -infinity to infinity. In other words, it's every single possible value, okay, as you go left to right. We also want to know what the range is. The range represents the y values, and the y values are also -infinity to infinity. And as an exercise, I'd like for y'all to stop for a second and ponder why would that be the case. And hopefully what you're saying is because this function is gradually going down over time, right, and is also gradually going up, the domain has to be -infinity to infinity. Okay? So let's go on to the next one. So that was our first one. The next one that we're going to deal with is what's called the quadratic. And by the way, this one here is called linear. Right? It's because it's a line. It's a linear function. So the next one is going to be the quadratic. An easy way to remember what the quadratic is, think of the second letter in quadratic. It's a U. Okay, so it's going to be U-shaped. But we're going to do the same exact thing. We have y equals x squared, so we're going to just, off to the side, we go x, y. And I'm just going to plug in values. We're going to go -2, -1, 0, 1, and 2. And let's just figure out what the y values are. What's -2 squared? 4. What's -1 squared? 1. What's 0 squared? 0. What's 1 squared? 1. What's 2 squared? 4. And we'll plot those points. So I'm plotting 0, 0 first. And then we have -1, 1. -2, 4, so 1, 2, 3, 4, 1, 1, negative 2, 4. Now this function, I'm sorry, 2, 4. This function is really cool because of the symmetry that it has. And what I mean by symmetry is that whatever you go to the left, you go to the right the same amount, right? That's how you know you're drawing it correctly, okay? So with this one, if I ask you what's the domain, again, you know you're going left to right, so this is just going to be negative infinity to infinity. And if I ask you for the range, this thing shoots up forever, but where does it start? It starts on the x-axis. So what we say is it starts at 0. We use the bracket to mean we include 0, and then it goes up forever to infinity. All right, let's look at the next one. So our next function that we care about is the absolute value. Okay, and this one is y equals absolute value of x. So again, if we go x, y, we're just going to use our points, negative 2, negative 1, 0, 1, and 2. We get the same thing, right? We get, except if it's negative, it's now positive. So the shape of this is going to be pretty much like so, okay? It's basically, it's a V shape, and the great thing about this one is that if we think about the general shape, it's pretty similar to the quadratic. So what does that mean about domain and range? That means the domain and range are going to be the same thing. And there's our answer. All right, next up we have the square root function, and that is y equals the square root of x. Now, for this one, we gotta have to pick different x and y values from the previous ones because we can't take the square root of a negative value, right? So we're going to start off, we're going to use 0, then we use 1, and then I'm going to use 4 and 9. And if you're pondering why, well, it's because the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. I picked values that give you exact square roots because if I, for example, pick 3, what's the square root of 3? It's not a pretty number, okay? So we'll plot these. So we got 0, 0, 1, 1, 4, 2. Let's see here, 1, 2, 3. Sorry, 1, 2, 3, 4, 2. Actually messed up there. 5, 6, 7, 8, 9, 1, 2, 3. And it looks something like that. So here, when we talk about the domain, this doesn't go on forever, right? If we go left to right, it starts at 0, and then it goes on forever, right? It starts 0, and then it shoots off to the right, okay? And the same thing's actually true for the range, right? It starts at 0, and then it gradually goes up over time, right? This keeps going up. It gradually goes up over time. So the domain and range of this function is exactly the same. It's from 0 to infinity. Cool. Let's look at the next one. So the next function we have is the cubic, which is y equals x cubed. So we'll go x, y. We're going to use negative 2, which is negative 8, because we can do this. Negative 1, which is going to be negative 1. 0, which is 0. 1, which is 1. And 2, which is 8. If you're confused with what I'm doing, I'm just plugging in negative 2, right? Negative 2 cubed means negative 2 times negative 2 times negative 2, which is negative 8. Negative 1 cubed is negative 1 times negative 1 times negative 1, which is negative 1, etc., etc. Okay? So we plot those, and then we're going to graph them. So let's go negative 2 and go down 1, 2, 3, 4, 5, 6, 7, 8. Got a point there. And then we go what? -1, -1. We got a point there. We got 0, 0, 1, and we got 8. 1, 2, 3, 4, 5, 6, 7, 8. And so we have something like this. And that's it. Now, this graph is really great for domain and range because you can see it shoots to the left and right forever and ever. And it also goes clearly up and down forever and ever. So both the domain and the range are the same thing. It's negative infinity to infinity. Okay? Cool. All right. Then the last one that is going to be extremely important to know is the reciprocal function. I'm going to mention a couple more. And the reciprocal function is y equals 1 over x. And with this one, if we plot points, this one's really interesting because if I go x, y, if I plug in -2, I get -1/2. If I plug in -1, I get -1. If I plug in 0, I actually get undefined. Can't do it. If I plug in 1, I get 1. And if I plug in 2, I get 1/2. Okay. Now let's start with this undefined business. Okay. So you can't divide by 0. So what this means is that you actually get an asymptote here. Okay. Now for reasons that we won't go into too much detail on here, we also have horizontal asymptotes. Okay, and if you're curious about this, ask me and I'll go into more detail about this. What I can tell you, kind of shorthand, why it is what it is that as you pick values of x that as x gets larger and larger, like 1/2, 1/3, 1/4, 1/5, 1/6, 1/8, you're getting lower and lower, and you're getting closer and closer to a value here. And that value that you're getting closer to is 0, right? But you never get to 0, right? Now on the flip side, if you take fractions like what's 1 over 1/2, it's 2. What's 1 over 1/3, it's 3. So on the other side, you're going to infinity. And the same thing happens on the left, okay? So we have something like so. All right. Now, this one's really interesting. Now, domain and range are actually the same thing, but the domain is going to be negative infinity to 0, union 0 to infinity. And I ask you to ponder for a second why that's the case. And hopefully what you're telling me is as you go left to right, it doesn't exist here. It doesn't exist at the asymptote. So we know that the domain doesn't exist there, and so that's the answer. And the range is actually the same thing. And as I write out the same thing over again, I hope that you sit here and ponder, why would that be the case? And that's the same reason. You have an asymptote here. It doesn't exist at 0. So basically the reciprocal function never exists at 0, but outside of that it can exist. And so we just exclude those values and then we're good to go. Cool. Now, there are some other functions that we're not going to spend a lot of time on. There is like an exponential, which is y equals 2 to the x. I'm just going to give you a quick sketch of what that looks like. It looks something like this. Basically, if as x plugs in negative numbers for x, you get closer and closer to 0. And as you pick greater and greater values, this thing for x, it's going to shoot up. This intersection point is 1 because when x is 0, it's 1. Okay, so this is called the exponential graph. And we're not going to do this. We're not going to play with this graph outside of me talking about it right now. But it does show up on the quizzes. It won't be on your test, but it does show up on the quizzes. So I want to make sure that you guys are aware of some of these other graphs. And then I think you also have the cubed root. And the cubed root goes something like this. Well, the cubed root is actually something called the inverse of the cube function. So basically, if you switch x and y, you're going to get this value. Okay, again, that's called the inverse. All right, looks something like this. As the inverse, you're switching x and y, so actually the domain and range are going to be the same thing. Okay, on the exponential, it's asymptotic, so it gets closer and closer to touching the x-axis, but it never does. Okay, so the domain would be negative infinity to infinity, but the range would be from 0 to infinity. And when we talk about the range, we would say parentheses 0 to infinity because it never touches it, right? While the domain is let you go left and right forever and ever. And I encourage you when you do this to not necessarily memorize these, but just think about it. Like look at the graph and think to yourself, well, what would be the x values that are possible? What would be the y values that are possible? Okay. All right, well, that's it, guys. That's all I wanted to do is make sure that you guys are cool with what these functions look like. Please make sure that you actually study through and know them. You need to become super familiar with them for the upcoming lessons. All right, that's it. Hope if you guys have questions, please reach out to me. Otherwise, I will see you in the next video.